proposal. This is my video 2 project for the ME210 course about the curvilinear motion of a toy train. So when it comes to real life example I created, it was a course about the curvilinear motion of a toy train. Here's a short video of the train. Here in this video you can see that it's simply a toy train going around a circle track multiple times. Using this video, we can create a list of given and assumptions. When it comes to the values such as the radius and velocity, I'll show my calculations later on. So we are given that the velocity of this train is constant at a constant velocity of 0.254 meters per second. Alongside that, the geometry of the track itself is also shown, with it being a complete circle, with a radius of 0.3239 meters. To make things easier to solve this problem, we can assume that tracks are frictionless, and we can ignore air resistance alongside any other small negligible different forces that may just make the problem harder to solve. We can say that the acceleration of the train itself is actually zero, since velocity is constant as well, meaning the acceleration is 0 meters per second squared. And lastly, we can assume that the train, in other words the engine itself, can be considered as a single particle. Here we can actually create a free body diagram of the problem itself. When it comes to the problem, we can say the problem would be is how to find the acceleration tangent. In this free body diagram, see the circle itself actually represents the track. Of course, we're given the information of the velocity and the radius, and from there we can actually figure out and chart out where the associated normal and acceleration tangent vectors would be. Here you can see some additional calculations when it came to how I figured out the radius of the track itself. Using this measuring app I had on my phone, I was able to figure out that the diameter of the track itself was 25.5 inches. When converting that, I got that the diameter is actually 0.6477 meters. It's from this I was able to do additional calculations. So you can see on the left side, you can see my calculation right here. Using the video itself, I was able to time how long it took for the train to reach 1/4 of the circle. Using that and the velocity equation of s over change in time, I figured out the velocity of 0.254 meters per second. And of course, using the diameter, I was able to find the radius as well. On the right hand side, we see some helpful equations that we can use to answer the question of how to find the acceleration tangent value. Of course, since we're given the radius and the velocity of this train in this problem, we can quickly be able to find the acceleration normal value. Using equations like the one underneath it, it can help us find and answer the question of finding what is the value of the acceleration tangent. In this problem, it goes over various different topics and concepts that are covered in chapter 13, such as Newton's second law, and the use of nt coordinates for motion, especially those in circular nature, as well as the kinematics of circular motion. Through this, you can see that this is a real-life example of the topics we covered over in chapter 13.